second video of chapter 3. Today we're going to be talking about section 3.2, which expands on a little bit of what we learned in section 3.1. And so we're going to be doing a lot of what we already did in 3.1, but this section is titled the second derivative test. So yes, we have to delve into the second derivative. Now, there may be questions of, well, why is that useful? Why would that help me? Why do I care? Why are you asking all these questions? I don't know. I'll explain it as we go, right? So, let's again consider a graph. I'll do, the classic kind of cubic graph. So, has a couple of extreme points and that we want to consider. Okay? When we take the derivative of this graph, right? If it's x cubed of some sort, right? Its derivative is going to be a polynomial, right? In specific, that polynomial is going to look something, right? Because it's increasing up until this point, right? So that means that my first derivative needs to be positive, okay? Between this point and this point, my graph is decreasing. So that means my first derivative needs to be negative. And, of course, after this point, again, it's increasing, so my first derivative needs to be positive, right? So let me make this explicit on the picture. This graph is f, and this graph is basically f prime. It kind of tells me what the slope of the graph is at that curve moment. Now, this may not be perfectly to scale, but it gives us an idea of what we're looking for. Okay? So what would getting a third derivative, or a second derivative do for us in this case, right? Well, let's add that color on here. Let's add that graph. So if I have a parabola, right, x squared, for example, the derivative of that is 2x, right? So that's a line, right? So if we're just looking at the first derivative now, it's decreasing from here until this point. So that means that my line should be in the negative region. And after it hits this point, it starts increasing, so my line should be in the positive region. Okay, so let's lay this out again. This blue line I just drew is f double prime. Okay. So all of that's placed on the picture, right? We have an idea of where f is, and we can kind of see how the pink purplish line tells us where it's going to be increasing when this graph is positive, decreasing when the purple graph is negative, and increasing again when it becomes positive again, right? But now let's cut out the middleman, so the f prime. So I'll erase that real quick. And solely take a look at how the line compares, right? How the derivative, the second derivative, right, compares with the black line, right? So notice, whenever the blue line is negative, our graph has a particular shape to it. It kind of has, it's as if we were holding a cup down, in a way, right? So I take a cup and I'm holding it downwards, right? It's kind of like a sad face, essentially. It's kind of frowning, right? So we put some eyes on it, it would be sad. Okay? That's kind of what this side looks like. Okay? The other side, the right side, right? It's kind of flipped around. Now my cup's being held up, right? So now it's a happy curve, right? So now we kind of have a more smiley face on it, right? So we have up like a cup, or up like a smiley face, I guess you want to, but up like a cup, down like a frown, right? And so we can see that the blue line, when the blue line's negative, it corresponds to when the black line is concave down, what we call kind of the frowny face part, the cup's holding down. And whenever the blue line's positive, then the black graph is concave up, we call it. Whenever we kind of have our smiley face, we have the cup being held up in that case. Okay? So, this is going to be useful to help us further graph these, get these graphs in as the best form as we can, right? Because that's going to be able to really tell me specifically how my curves move, okay? So we're going to see a couple examples with this. And this is going to kind of lead into our second derivative test as we go through, right? So, first, let's talk about the second derivative test, right? Last time we had two examples. The first example was x squared minus 2x plus 3. Maybe it was plus 4. Yeah, I think it was plus 4. And the second example was x cubed minus 6x squared plus 9x. Okay. Whenever we were finding the critical points of these values, or determining what the critical points we're doing, right, we would do the first derivative test. So we would find their first derivative, set it equal to 0, and then we would kind of test values on each side of that 0 point to be able to draw our number line to see when one would be increasing and one would be decreasing, right? However, so we still need to take the first derivative and see when the values are 0, right? So if you recall, right, f prime of x in on the left side case was 2x minus 2, and so we got that our critical value was x equals 1, and that our critical point overall was 1, 3. Okay? Now in this graph, right, you'll recall that the derivative was 3x squared minus 12x plus 9, and that f double prime of x, we didn't do f double prime of x yet, that we also could we factored this, right, into 3 times x minus 1 times x minus 3. And so we got that our critical values were x equals 1 and 3, and that our critical points were 1, 4, and 3, 0. Okay, so those were our critical values and our critical points in that case, kind of the points that correspond with the values. Now, what we're going to see, right, is as we said last time, right, we wanted to do the number line, right, and still this could be useful. If you like doing this, then absolutely keep doing that, because honestly I still do it as I work through. So kind of plotting your critical points, critical values onto the number line, and then seeing what's happening to the left side. So you remember that it was at 1 we had that the graph was decreasing beforehand and increasing after, right? And so 1, 3 was a relative minimum in that case, right? I'm going through all this again just to show that the second derivative test will also show the same results when we get to it. Again, 1, 4 and 3, 0, right? We saw that 1, 4 was a relative max because it was increasing before and decreasing after, and that 3, 0 was a relative min because we were decreasing before and increasing after, right? And so that's how we could figure out what was going on with these points. So that's a relative max here. This is a relative min here, in order to know how to sketch our graph. But now there's another thing that's going to become useful to us, right? Which is the second derivative test, which I will do in a color. Let's try blue. Second derivative test. So how the second derivative test works is I need to find, of course, first the second derivative, right? So for number 1, right, what is my second derivative in this case? So it's going to be the derivative of 2x, which is 2. And it's going to be the derivative of negative 2, which is 0. So we just get f double prime of x is 2, right? So what exactly does this tell us, right? Clearly, if I plug any point in here, even 1, right, I'm going to get 2, right, because it's always 2. What that means is that my graph at that point, if this number is positive, if this number is greater than 0, when I plug in the x, which in this case is always going to be 2, then my graph is going to look like this. It's going to be up, like the happy face, right? It's concave up like a cup. Okay? What that means for our 1, right? Just looking at the picture, right? If that 1 is a kind of a critical point on the graph, then it has to be a relative minimum, right? Do you see that? Because the graph is concave up, and so we can't have a maximum with something that's concave up, right? It has to be at the bottom, right? It would be here. So in this way, we can also tell that the 0.13 is a relative minimum. And in that way, we can do slightly less computations, okay? To get a better example going, let's come over here to our cubic one, right? So f double prime in this case is going to be, so let's use this equation here, right? The derivative of 3x squared is 6x, and the derivative of negative 12 x is negative 12, and the derivative of 9 is 0. So we get 6x minus 12, right? So what happens when I plug in 1 and plug in 3? Well, when I plug in 1, I'm going to get 6 minus 12, which is negative 6. And that's less than 0. And when I plug in 3 into f double prime, I get 6 times 3, which is 18. 18 minus 12 is 6. Which is, so this one's less than 0, right? And this one's greater than 0. What does that mean? Well, we already know what happens when it's greater than 0, right? And we're going to get a graph that looks like this, right? It's going to be concave up. So if my graph is concave up, that means that this point is a relative min, right? Which we've already shown above, but we can quickly use the second derivative, knowing when something's concave up and concave down, to tell for sure that if this is some sort of critical relative max min point, then it has to be a minimum. Good. On the left here, right, f double prime of 1 is negative 6, right? This is going to be the opposite. If I'm less than 0, then it's going to be concave down, like the frown, or by holding the cup down, right? In the context of our graph, our point then has to be at the top, right? At kind of the top of that curve. It has to be at the tip point, which makes it a relative maximum. So that's why 1 is a relative max and 3 is a relative min, right? So both tests are viable. This was the first derivative test. This is the second derivative test. So it's your preference. But this is very valuable, you know, to see clearly what's exactly happening maybe around that point, or what the concavity is, because then you can easily see what's happening, like, or what the curve looks like at that point, so you can tell if it's a max or a min. Good. Now, that's not all the second derivative can do for us, right? The second derivative so I'm going to focus in a little more on the cubic example we had. So the f of x equals x cubed minus 6x squared plus 9x. F prime of x is going to be 3x squared minus 12x plus 9, right? And so we learn from here, right, doing either first or second derivative test, that 1, 4 is a relative max, and 0, 3 is a relative min. Now this was enough for us to graph before, but let's see if we can't do it a little bit better, right? So again, we found the second derivative when we were testing out the second derivative test, and this was 6x minus 12. Now, there may have been some thoughts whenever we had pulled this up the first time, right, or we got this, to say, oh, well, maybe would I take that and set it equal to 0? Similar to what we do when we take this and set it equal to 0. Well, we actually will. But that won't give us critical points. This will give us something called, if we set this equal to 0, this will give us something called inflection points. What do we mean by inflection points? Well, when we're talking about critical points, right, our extreme values, right, those are telling us when we change from being increasing to decreasing, or change from being decreasing to increasing, right? Where you got on top of the slope and then went down, or when you got to the bottom of the valley and then came back up, right? Inflection points don't tell us when we're increasing or decreasing. They tell us the changing point when we're going from concave up to concave down, right? So, at an inflection point, so let's say this is an inflection point, before that point, my graph may be, kind of having a frowny look to it, right? It's kind of down. We're holding the cup down. It's concave down at this point. But after that point, my curve may shift around. And so now it's going to be facing upwards, right? It's going to be concave up like a cup. It's going to be moving upwards in this way, if that makes sense, right? And so that's what inflection point does. It tells us when we go from being concave up to concave down, and from concave down to concave up. Okay? So we can find that point on this graph by taking our second derivative and setting it equal to 0. So when we set it equal to 0, right, I'm going to get that 6x equals 12, which means that x equals 2. So x equals 2 will give us an inflection, the inflection value, right? And to get the inflection point, I'm going to plug that into my function. So inflection point I'll write up here. I'm going to I need to find 2 and f of 2. So let's see, f of 2 is going to be 2 cubed is 8. 8 minus 6 times 4 is 24. That's going to be negative 16. Negative 16 plus 9 times 2 is negative 16 plus 18, which is 2. How about that? Some pretty nice numbers in this case, luckily, so nothing too bad here. So we get the point 2, 2. So 2, 2 is where there's a change happening, right? Now we need to figure out, well, what exactly is the change, right? To do that, we're going to create a number line, but instead of this being for my first derivative, right, as the first derivative test did, this is going to be purely for doing inflection point, second derivative, right? So I'm going to put 2 on the line, and I'm going to look to the left or right to see what's happening, right? When I look to the left, right, so let's take 0 for example, because 0 is less than 2, and plug it into the second derivative. If I plug 0 into 6x minus 12, I get 6 times 0 minus 12, which is negative 12, right? So that means that my graph is negative, right? So we get negative values on that side, which means that not that I'm decreasing, but that I'm concave down at that point. Good. What about after 2? Well, if I go after 2, right, that means that I'm taking the number 3, for example. Plugging it into the function, I'm going to get 6 times 3, which is 18. 18 minus 12 is 6, right? And so on that side, I get a positive value, which, as we've already seen, that's when I'm going to be concave up. Good. So before 2, I'm concave down, and after 2, I'm concave up, right? So let's take our knowledge of the relative maxes and mins along with my concave down, concave up stuff and put it onto a graph. Good. So I'm going to graph all my points again, right? So we have the point 1, 4. Put it here. We have the point 2, 2. And we have the point 3, 0. Okay? Remember, before we get to 2, we're concave down, right? But 1 is a relative maximum. So we know that we are increasing before we get to 1, and then we have to decrease afterwards because it's a relative maximum. But we're still concave down, right? So we want our curve to kind of have the downward shape in that case. After 2, I'm concave up, right? And that's going to match, right, with 3, 0 being a relative min, or 0, 3. Or, sorry, I put 0, 3, that should be 3, 0. Whoops. Sorry. Those of you who watch the last video, so 3, 0 is my relative minimum, right? So I'm going to go down to that point and then come up, right? Because that's kind of the lower end at that moment. But my curve should have a relative, should have kind of an upward look to it at this point, right? Whereas this side has the downward look. And 2 is the point where that all changes. Okay? So in all of this, this really helps me to get a full idea of, you know, what exactly I'm doing with my curve and how to perfectly um, how to get all the curves right and make it work. Okay, good. So let's do one other example, and we'll go through and just do all the steps that you do for curve sketching, and then we'll leave it there. The book, if you're interested, kind of has a list of things for you to go through to know curve sketching, and it adds kind of a step 5 to look for certain details. I would invite you to investigate those and learn that on your own. That's going to be kind of outside of the time that we have for the course at the moment. So yeah, we're going to focus on kind of these more polynomial examples in general. Okay, so let's do, example, our big example here. Well, f of x is going to be, let's see, let's study x to the 4th power minus 4x plus 3. Okay, good. So the first step, right, is we're going to work down to the first derivative, right? So f prime of x is going to be, right, because we're wanting to curve sketch this. We want to make a sketch of this curve. So f prime of x in our case is going to be 4x cubed minus 4 plus 0, right? Now, I can take this curve, and I can set it equal to 0, and as we typically do, you know, we can do our factoring magic, or we can just see if there's an easy solution, right? Which in this case, it looks like there might be. Because I can take a 4 and add it to both sides, right? So I'll take, so this will be 4x cubed equals 4, but that's the same thing as x cubed equals 1, right? Just divide a 4 from both sides. So what is x supposed to be? Well, x is 1, which may have been really easy to see from the equation itself, but we're going to see, you know, clearly here that x is 1 is a critical point, right? So from here, we can of course, we can figure out what the value is, right? So 1, so we have a critical point, which is going to be the point 1 and 1 minus 4 plus 3, that's 0, right? So 1, 0, we have a critical point. Now the next step would be to figure out, well, is that a relative max or is that a relative min? I'm going to show both the first and the second derivative test, but you have a preference to which one you'd rather do. So, first derivative test says that I need to take my value, my critical value, 1, put it on the number line, and test each side, right? So let's plug in a number. So reminder, our derivative in this case is 4x cubed minus 4. Let's take a number to the left and see what value we get. So easy example is 0. What's 4 times 0 cubed minus 4? Well, that's minus 4, right? So on the left side of 1, we are negative, right? Keeping in mind again, this is for f prime. And since it's negative here, we are decreasing. Not concave down, decreasing, right? Because we're doing the first derivative, not the second derivative. Okay? After 1, you might guess, but when I put 2 inside, I get 4 times 8 minus 4, which is going to be 28, but that's clearly bigger than 0, right? So that's positive, so we're increasing after 1. Good. So from the first derivative test, right, so this is f dt, right? What would I say about this point? That it's a relative minimum. Okay? So this is all old stuff. This is stuff we've done before. So let's do new stuff in another color. So we're going to have the s dt, second derivative test, as well to check. So you can do this one, which we've done before, or we can do this one. The second derivative test says that I take the second derivative of my function, right, which in this case is going to be 12x squared, right? So this is f double prime of x, and I plug in my critical value, which in this case is 1. So we're going to plug in f double prime of 1, which is 12. Now is 12 greater than or less than 0? It's greater than, right? Greater than 0. So that means that at that point, my graph is concave up, and so that implies that 1 is a relative minimum. Good. Okay, so we figured out that 1, 0 is a relative minimum. That's our critical point. So let's move on and do the second derivative, right, which we found over here, but you may not have, depending on if you did the first derivative test. But f double prime of x, regardless, is 12x squared. And now, to figure out my inflection points, I'm going to take this and say it equals 0. Well, what x will make that 0? Well, 0, right? X is 0. Right? And you can check that if you want to, but x is 0 is going to be the only solution in that case. So, x is 0, so what happens when we put 0 inside f of x? We're going to get the point 0, 3. So this is it should be an inflection point. Let's check to be sure. 0, 3. We're going to do our number line, right? So this number line was for f prime, and now we're going to do one for f double prime. So here's 0. Let's test the number to the left of 0. Well, if I test the number to the left of 0, it's going to be, right, negative 1, for example, it's going to end up being positive, right? Good. Okay? And let's test the number to the right of 0, right? Clearly negative 1 squared is 1, so we get 12 times 1, which is positive. And then if we do 1, right, we get 12, which is also positive. So notice on both sides of 0, we are concave up. So what does that tell us about that point? Is it an inflection point? What is it? Well, it's a significant point on maybe in terms of our second derivative, but it's not directly a inflection point, right? This is similar to when we did x cubed in the last video, that even though we got 0 as a critical point, our function was always increasing still. And so we have something similar here. So this might be a good point to graph, but the concavity is not going to change at that point. Okay? So let's take our graph and put both of our points on here now. So we have the point 1, 0, and we have the point 0, 3. Right? We are always concave up on this graph, but maybe keeping special note on that 0 point, which is a little odd, right? We're always going to be concave up regardless. Except some weirdly did happen, but that's okay. So we can draw something like this. Okay? So we're concave up before 0, we're concave up after 0, as we should be, right? Just make that look good. And then after 1, right, so we're decreasing before 1, and after 1 we start increasing. And so that is a good rough sketch of maybe what our graph would look like. Okay, good. Well, that's all I have to say. Thank you all for watching. Hopefully that helps with curve sketching. Always feel free to reach out. Tune in for next video where we're going to be covering optimization, kind of taking some of this idea and putting it into more real-world applications. But this is also useful in the real world. So, yeah, thank you for watching. Have a great night. Have a great day.